Okay, well, I'm going to go ahead and get started. Can the people on Zoom see the PowerPoint in the normal presentation view?
Now we can't hear you properly.
You cannot?
Before it was better.
Okay. What is is there an echo?
Yes, a little bit.
I'm gonna try it without the mic. How's that?
Now it's better.
Okay.
Now it's okay.
And my audience here can hear me fine? Yeah. Okay. And the people in the back? There's nobody in the back.
Ah, okay.
Okay. All right. So let's go ahead and get started. This is the last day, day 3 of our electrochemistry crash course. And today we'll cover some special topics which were voted on by participants. And so to summarize what we've been through the last few weeks, the first day we went through electrochemical thermodynamics. We understood free energy and electrochemical equilibrium. Last week we went through kinetics, both Faradaic and non-Faradaic current. We discussed the electrochemical reversibility of reactions. We learned a little bit about mass transport, and we covered both potential step and linear sweep and cyclic voltammetry. The special topics that we will discuss today are converting between reference electrodes, junction potentials, bulk electrolysis and Faradaic efficiency, the design of electrochemical cells, photoelectrochemistry, electrochemical impedance spectroscopy, and lastly, we'll quickly go through potential-dependent current and the analysis of Tafel slope. So a quick review of thermodynamics. Here we have our relationship to Gibbs free energy. We have the definition of the standard cell potential. We have the Nernst equation relating concentration of reactants in electrochemical equilibrium to cell potential. And then lastly, we have the summation of electrochemical reactions to yield a cell potential. And we looked at the example of our zinc copper battery. Quick review of kinetics. We remember that the electron transfer always occurs at the interface between the electrode and the solution. We discussed that there are 2 primary sources of electrochemical current. The first that we primarily care about is Faradaic current, where there's a formal electron transfer to a redox active species in solution. This is typically our analyte of interest. And non-Faradaic current, where current flows from the migration of ions in solution. And as discussed last time, we remembered that electrode kinetics are determined in large part by mass transport. We have migration of ions, charged particles in an electric field. We have convections, which would be related to stirring. And we have diffusion of the analyte to the electrode. So last week I gave you all some practice questions. I hope you had a chance to go through them. If not, here's the reveal. So I gave solution parameters here. We have 0.1 molar potassium chloride with iron ferricyanide dissolved in it. I gave you the area of the platinum electrode and the diffusion constant of iron ferricyanide, the solution resistance, which we can measure, and the double layer capacitance. And the first thing I asked to do in a potential step is to predict what the current would look like, and that's shown here. We see that it decays logarithmically quite quickly, and within 1 millisecond, it's decayed almost to 0. I ask you to do the same thing for the Faradaic current using this equation here, the Cottrell equation. And we see here that the initial current's a little bit slower, but it decays also slower. I wanted you to plot a linear combination of the two, shown here in gray. And I asked which current dominates at short times, and you can see that the double layer capacitance shown in blue is dominating at early time. And then if we zoom in and we look at longer times, we can see that the Faradaic current dominates at times longer than 1 millisecond in this system. Now, I'd like to point out that in any other system that you have, that exact time constant will differ depending on the solution resistance, the capacitance, the diffusion, and all of the other parameters that we've looked at. However, the Faradaic current dominating at longer times is especially true if you are stirring. So if you do a potential step, if you're doing a bulk electrolysis, you will almost always see a spike in current which will decay quite rapidly, and then all of the current that you see from the first few seconds will be attributed to Faradaic current. The next question I asked, I wanted us to look at the same solution and do linear sweeps conducted at various scan rates and predict the double layer capacitance. And as I mentioned last time, the current is actually proportional linearly to the scan rate. And we can see that shown here as we decrease the scan rate, the non-Faradaic current contribution is simultaneously decreased along with it. I asked you then to predict the peak current for this species, and I gave you this equation here, and I would like to point out that the peak current is actually proportional to the square root of the scan rate, so it doesn't increase as quickly, and that becomes important because we can see at fast scan rates, there's a lower ratio of the Faradaic current to non-Faradaic current. Now, in all of these cases, the ratio of Faradaic current is much greater than the non-Faradaic contributions. Now, I wanted to imagine a case where the analyte is sparingly soluble, which can be quite common for organic reactants. And if we consider that many organic solutions will have a very large solution resistance, this can become very problematic because we can see that at fast scan rates, the amount of Faradaic current can actually be lower than the non-Faradaic current. So this can become problematic when we're doing analysis in non-aqueous solutions. So moving forward, the topics for today I mentioned, let's move into the first one, converting between reference electrodes. Now this, if you do electrochemistry, I guarantee you will have to do. And I do note that it can be a little bit tricky, and you have to kind of think a little bit when you're doing this, conversion. So my saying is, when in doubt, draw it out. So if you're not sure, what you can do is you can draw the energy scale of, let's say, the potential that you know, and the same energy scale as the potential that you will convert to. Now, you can look up the conversion between NHE and SCE. And we have here that at 0 volts versus NHE, the SCE potential, that's saturated calomel electrode, occurs at minus 0.241. Conversely, in NHE, at plus 0.241, we have the 0 volts versus SCE. And so there's always a difference of 0.241 volts between these two. The question might be, do I add it or subtract it? And that's why I like to draw it out, because once you draw it out, the answer becomes clear. So if I tell you that iron ferricyanide has an E0 of 0.361 volts versus NHE, I can ask, what is its E0 versus SCE? And so we have shown here 0.36, and we can kind of interpolate where this might be. We know it's not going to be a negative number. It's more positive than 0. we know it's not going to be huge, it's not going to be 0.8, and the correct conversion is a subtraction of 0.241 volts, and indeed the E0 of ferricyanide versus SCE is plus 0.12 volts. So another reference electrode that's very common that we use a lot in artificial photosynthesis is the hydrogen electrode. So the standard hydrogen electrode uses an activity of 1 molar H+. The normal hydrogen electrode uses a concentration of H+ of 1 molar. So obviously those are going to be quite close depending on the activity coefficient. And most of us use NHE for simplicity. But if you're getting into some thick analytical problems, you might consider the activity of H+. And the next one that can be very tricky is the reversible hydrogen electrode, because that is actually a pH-dependent electrode. So the reversible hydrogen electrode can be thought of as the hydrogen evolution reaction that occurs reversibly as a function of pH. And the way that we convert is we take to calculate the voltage versus RHE, we would take the voltage measured versus NHE and subtract 0.059 volts for every pH unit. Remember last time I talked about how 0.059 volts is similar to a pH unit, and you can see that relationship here. Because for every order of magnitude change in pH or a change in H+ concentration, we shift the thermodynamic potential by 59 millivolts. So this is a very useful equation, and what it effectively produces is a plot. If we look at the hydrogen evolution reaction and oxygen evolution reaction versus the pH, we can see how their thermodynamic potential versus a pH-independent reference electrode shifts. But in all cases, the difference between the two of them is 1.23 volts that we always quote as the thermodynamic potential for water splitting. So if I'm at a high pH, it's easier, that is, it's more negative to do water oxidation, but then we could say it's harder, that is, again, more negative to do hydrogen reduction. But again, always 1.23 volts difference. And I have a reference electrode calculator that I've made in Excel. You can also find other ones online. I would always double check if you make one yourself in an Excel spreadsheet or you're trying one online, double check them, because there can be little mistakes that can really mess you up in those calculations. Moving on, the next topic is liquid junction potentials. Now, this is something that occurs, and typically we try to minimize it in electrochemistry. So a liquid junction potential is actually a chemical potential that occurs when two electrolytes of different composition come into different composition or different concentration, and when they come into contact. So there's a few main types. The first one is the same electrolyte at different concentrations. So if we have a solution of 0.01 molar HCl and a solution of 1 molar HCl, we can see that there's a chemical driving force for the H+ and the Cl- to move across some membrane or some junction. Now the arrow shown for H+ is larger because H+ has greater mobility. It's smaller, it has a lower hydrodynamic radius, and it moves quicker. That difference in mobility will become important. So if we take a look at the second type, it's the same concentration on two sides, but with one common ion. So we have 0.1 molar HCl, 0.1 molar KCl. Again, as the system attempts to reach chemical equilibrium, we have different mobilities of these ions. H+ moves faster towards the right-hand solution, and K plus moves slower towards the left-hand solution. The last case to consider is where nothing is the same. We have two solutions, different concentration with different ions. Again, all of these ions will have different mobilities. The differences in these ionic mobilities can lead to the accumulation of charge on either side of this junction. And so if we look at our type 1, we see H plus moves faster towards the left. We will accumulate a positive charge on the left-hand solution, and we'll accumulate a negative charge on the right-hand solution. For type 3, again, H plus is the fastest moving ion. We accumulate positive charge on the right-hand side. And again, for this last case, H plus moves the fastest. We accumulate positive charge on the other side. Now, this assumes a difference in the mobility of ions. If ions all have the same exact mobility, there will be no junction potential. And this is also a transient phenomenon. If the system is allowed to equilibrate, then there will be no junction potential. And so a general equation that we can use is that the junction potential is equal to the difference between the transference numbers of these ions, the transference number being related to the mobility of each of these. I'm not going to define this precisely today, but it's related to the difference in the mobility of these ions. Again, if they're equal, that value is 0. If we have equal mobility of all ions, there is 0 junction potential. The A1 and A2 are the mean ionic activity for both of the solutions. So if they're diluted to infinite, if they're both diluted to the infinite dilution, or if they're at the same concentration, then again, the junction potential will fall to 0. So moving on, many of us do bulk electrolysis, especially if we're doing catalysis or electroorganic synthesis. This is more of a, like I said, a bulk technique. So it's a technique that aims to change the concentration of a redox species in the bulk of the solution. So an example would be, our ferrocene example is if we prepare a solution of iron to ferrocene, and we want to convert all of it in solution to iron 3. So then we would electrolyze for a long time in order to accumulate iron 3. Now, if we did this with a normal working electrode, like I've shown here with a disc, that will take a very long time, because all of the redox active species have to come into contact with this small electrode. So typically we use a larger electrode. You might see one like this, or oftentimes you could see a porous material like carbon cloth or carbon paper. A lot of researchers use carbon nanotubes. You can use nickel foam. A whole lot of ideas about how you can increase that surface area so that the reaction moves quicker. Faradaic efficiency you can think of as yield. What is your product yield? But in the case where electrons are the limiting reagent. So in other words, I put in 1 mole of electrons, what is my yield of product that I get out? The percentage of that is the Faradaic efficiency. So it's the mole of product divided by the mole of electrons times 100%. Obviously, we all want 100% Faradaic efficiency. Just like in all of our reactions, we want 100% yield. So taking an example, one that we may be very familiar with is the oxygen evolution reaction. Another one that might be interesting is the CO2 reduction reaction. Today I'm only going to cover OER, the oxygen evolution reaction, but if anyone's interested, we can speak later about the CO2 reduction reaction, because that one's a little bit more complicated. But if we look at this reaction, as I mentioned here, it's the bottleneck of electrocatalytic water splitting. So if we want to produce hydrogen from water, we have to do this reaction efficiently. And we want to know, if I count electrons, what percentage of those electrons go to making oxygen? Because if that's not a large Faradaic efficiency, where did the electrons go? Did I decompose my catalyst? Did I decompose the electrode support? Did I have some other reaction going on? I want to know what my Faradaic efficiency is. So let's take an example. Let's say I develop a catalyst that can achieve 10 milliamps per centimeter squared. We're not going to care about potential right now. It's a pretty small electrode. I electrolyze for 5 minutes in a 20 milliliter solution. And then I measure the oxygen concentration, and it starts around 20 micromolar and ends at 195 micromolar. And I can ask, what is the Faradaic efficiency of this reaction, of this bulk electrolysis? So as with any yield, you would say, what is the theoretical yield of oxygen? So first we'll determine the total charge. So we'll take 0.01 amps per centimeter squared. That's the current density. Remembering that amps is coulombs per second. So multiplying by the surface area of the electrode, multiplying by 5 minutes, converting minutes to seconds. All of the units cancel, giving us 1.5 coulombs. We can convert this total charge to moles of oxygen. We use 1.5 coulombs divided by Faraday's constant, which is in units coulombs per mole of fundamental charge, i.e. electrons. And as I noted up here, this is a 4-electron process to get oxygen. So I need 4 electrons per mole of oxygen. And so that gives me a theoretical yield of 3.9 micromole of oxygen produced. Now, obviously, all I have to do is determine how much I actually produced. So what is the measured yield of oxygen? We just determine the concentration change. We produce 175 micromolar. We know it's 20 milliliters. We measured 3.5 micromole of O2, and we determined a 90% Faradaic efficiency. Now, one thing that can be really tricky in oxygen evolution is that oxygen, as you probably know, is a gas. So it can easily escape from the reaction. And I kind of tilted the scale in our favor because this is actually within the solubility limit of oxygen. So in this example, we looked at the oxygen that was still in solution. And my preferred method for measuring oxygen is to have 0 headspace. That is, there's 0 gas. It does not equilibrate with the headspace. We're measuring the oxygen in the solution. You may not have that luxury. If that's the case, then you measure the oxygen in the headspace, and you can use Henry's law to determine what percentage of oxygen is still dissolved in solution, and do a summation of the oxygen in the headspace and the oxygen dissolved in the solution. So let's talk a little bit about electrochemical cell design. This is kind of a more practical part. So most of the time, researchers are studying one reaction, either an anodic oxidation or a cathodic reduction for some goal. Maybe they're studying both, but I am sure that it is easier to study one at a time and then put them together than studying both reactions at the same time. So if we consider that we want to do hydrogen production at the cathode here, I mentioned last week that our counter electrode is used to complete the circuit. So however many electrons flow out of or flow into this electrode for hydrogen reduction have to flow through the counter electrode as well. And I can ask, what's preventing the hydrogen from diffusing over there to be reoxidized? Is there anything in this cell? There's nothing. So I can produce hydrogen successfully, maybe at 100% Faradaic efficiency. It goes to my other electrode and then it's oxidized. So then I have a lower Faradaic efficiency and I have a reduced product selectivity. Also keeping in mind that in most electrochemical systems, when a 3-electrode setup is used with a reference electrode, a working electrode, and a counter electrode, we are not typically controlling the potential of the counter electrode. The counter electrode is used to supply current. So while our working electrode may be at some reasonable potential, our counter electrode might be at a very high potential. Indeed, I've seen reactions where my synthesis is happening at 1.8 volts versus silver chloride, and my counter electrode's at like minus 18 volts because I was in a non-aqueous solution passing a high amount of current. And whatever reaction was happening at the counter electrode, it had to apply a huge voltage just to match the current that I needed. And in that case, I'd see a bunch of stuff coming off the counter electrode. So the easiest way to kind of clear that up is to use a U-cell to separate the two compartments. And you have them separated with a membrane, which can be just a fritted glass filter. And then you have the two chambers separated. So here I have my cathodic compartment and here I have my anodic compartment. One key thing to keep in mind when you are using a U-cell is that the working electrode, this is a black glassy carbon electrode, is in the same compartment as your reference electrode. You might not be able to see it here, but the reference electrode is as near as possible to the working electrode. And in this case, my product is the white precipitate that's starting to come out. And so in this case, a simple glass fritted filter is sufficient to prevent product crossover to the other side. Oftentimes, a fritted glass filter is enough to just slow it down. If your reaction happens quickly, if your electrolysis is only 2 hours, then maybe a fritted glass filter is enough. But maybe you need to do something a little bit longer, or maybe you're one of us who is doing hydrogen evolution or some other fuel cell type reaction where you really cannot have crossover. In that case, your membrane could be an ion selective polymer, which leads us to the design of membrane electrode assemblies. And so in a membrane electrode assembly, electrocatalyst is deposited oftentimes directly onto the ion selective membranes. And the key thing being is the minimization of resistance and preventing gas crossover. You don't have to put the catalyst directly onto the membrane, although it is preferred. One of the favorites is Nafion. It's a proton-conducting fluoropolymer, and it's very, very common in proton exchange membrane electrolysis. If anyone ever sees the folks from my group, including myself, working in the high-pressure lab up here, that's what we are working on. We are working on membrane electrode assemblies for water splitting. And in this case, catalyst is loaded on both sides of the membrane. So here, the tan part is our membrane. In this case, it would be Nafion. And then a catalyst is sprayed directly onto that. And you usually add a binder which holds the catalyst together, such as Nafion. You could put Nafion in a solution form. Nafion is not water soluble, but it's soluble in other solvents. And then you would add an electrical contact that serves as both a metallic electrical contact, but also allows liquid to flow to the catalyst surface and gas to diffuse away from it. And this is called a GDL, a gas diffusion layer. But typically it has to be something that's highly electrically conducting, because any electrical Any poor electrical contacts will manifest itself in a higher overall resistance, resulting in voltage loss across the membrane. And so in this case, a GDL might look like a mesh grid here. So this is one of our titanium GDLs that we use. And in the end, the membrane is put together and compressed with two pistons, for example, titanium, and they're held together. And in this case, liquid flows into the anodic side of the cell here and flows back out of the cell on the other side. And on the cathodic side, we can have liquid flow in from the bottom and out of the top too, and we can collect the gases on either side of it. And the protons simply move across the membrane, completing our electrochemical circuit. And we could spend a whole year on this topic, but we'll spend one slide instead. So another topic that seemed interesting, that again could be at least one PhD thesis, probably entire career, that we'll cover in 2 slides, is photoelectrochemistry. And in photoelectrochemistry, we take advantage of the fact that absorbed electrons are absorbed and put an electron into a higher energy state. And so typically it's done with a dye or photosensitizer that's immobilized onto the electrode. A semiconductor can also be used, where instead of a HOMO-LUMO gap, we have the valence band, conduction band, and we have the band gap between these two energy states. But it's possible to do it with freely diffusing dye as well in solution. So you can have a dye in solution. The concept being the same, that when a photon is absorbed, it excites an electron from the HOMO to the LUMO, or the valence band to the conduction band of the semiconductor. Now, in this excited state, it's kind of interesting because this excited state makes the molecule or semiconductor both easier to oxidize and easier to reduce. It's easier to oxidize, that's a little bit easier to see because you now have this electron that's higher in energy that can easily transfer to an electrode. Being easier to reduce is perhaps a little bit tricky because the electron, instead of going into the LUMO, will actually go into the HOMO, which is a lower energy state. Kind of interesting. So this excited state electron can go from the LUMO into the electrode, or some vacancy that's very common is to take advantage of vacancies in a semiconductor material. Or an electron can be injected from a catalyst into the HOMO. So for example, if we wanted to do oxidative catalysis, for example, oxygen evolution reaction, from this excited state, the electron could transfer to the HOMO, and then we have the oxidized form of the catalyst, which can be used to drive our desired reaction. And then the electron from the LUMO can be injected into the electrode, or into the electrode, travel to the other electrode, and complete our electrochemical circuit. One thing that we always want to avoid and researchers are studying is avoiding recombination pathways. And so recombination can occur just in this example in a number of ways. The most simple one would be a relaxation, going from the LUMO back to the ground state, which is often why a electric field is applied on the electrode, because if we made this more positive, let's say if we made it more positive of the HOMO, for example, then there's a lot more driving force for this electron to transfer into the electrode rather than just simply recombine. Another potential pathway is actually an electron transferring from the electrode to the HOMO. Again, depending on applied potential. If we don't apply any potential, this is probably a very likely pathway. And lastly, even if we have the successful electron transfer from the catalyst to the HOMO, there's still a possibility of an excited electron traveling to the catalyst. And so it all depends on the relative rate constants and energetics of the intermediates. So when designing a system, these are things to consider, because you want your electrons to flow one way, but and although the thermodynamics may be on our side, we have to consider the kinetics. And oftentimes the kinetics are related to physical proximity. If the electron is very close, if the excited state electron is very close to the electrode, it's a lot more likely to successfully transfer into that electrode. Changing topics now, electrochemical impedance spectroscopy applies a sine wave at different frequencies, usually around 5 millivolts, usually from the millihertz to kilohertz range. And what it measures is the phase-sensitive current response. So if we have some voltage perturbation occurring here at some frequency, there could be a phase-sensitive current delay that occurs. And so for each frequency, we plot the imaginary and the real impedance components. So when we see an impedance plot, we're actually looking at a projection with the z-axis being the frequency. We're looking at the projection onto the complex plane. And what it can give you are factors such as the solution resistance, the polarization or charge transfer resistance, as well as the double layer capacitance. All parameters that may be of interest to your studies. And typically the data is fit using an equivalent circuit diagram, where we treat certain aspects of the electrochemical cell as if they were electrical components. The most common one being the Randall circuit, where we have this solution resistance that's in series with a parallel circuit that is both the charge transfer and the double layer capacitance. So you can think about this as the bulk solution, and then this is the electrode solution interface. And as it manifests itself typically is this semicircle. And the solution resistance is typically the real impedance at high frequencies. So in general, high frequencies are at lower impedance, and it moves to lower frequencies as you move to higher impedance. And the double layer capacitance is related to the frequency at the pinnacle of the semicircle. Now, using an equivalent circuit diagram has limitations because these components do not always act precisely as an electron would flowing through a material, like a resistor or a wire or a parallel plate capacitor. These are electrochemical systems, and they do not behave precisely like electrons would in a circuit. So one common thing that you will see added is the Warburg impedance, and the way it physically manifests itself in this Nyquist plot is a straight line in the low frequency regime that's usually at 45 degrees phase angle. So it's going off here at low angles, and it's related to diffusion controlled processes. Now, there's a lot more you can do with electrochemical impedance spectroscopy, especially if you have several semicircles. You can start to fit and try to understand your electrochemical system more intimately. But one thing I would mention to watch out for is that we are fitting these with an equivalent circuit diagram. They do not necessarily have the same physical meaning that we might assign to a circuit. And as we add more components, the fits will become better and better, but that does not necessarily mean that we are more accurately representing our electrochemical system. And I have seen some studies attempting to do electrochemical impedance fitting using electrochemical parameters such as rate constants, diffusion constants, etc. So our last topic for today our Tafel plots and the overpotential dependence of current. So the first day we talked about how the Nernst equation predicts the thermodynamics and the electrochemical equilibrium. Now it's nice, as we all know, if things occur in equilibrium, but we also know that most things do not occur with infinitely fast rate constants, and there's usually some energy barriers. And so the electrode kinetics that we observe are often drastically different than what we might predict from mass transport limitation, because there's some energy barrier. So we have to get over an activation energy in order to drive the electrochemical reaction. And so if we try to describe mathematically a relationship, we can use the Butler-Volmer equation, which basically states that the current we observe is equal to the exchange current times this factor. Now, the exchange current is a very important parameter for a lot of systems, because what the exchange current is the amount of current that passes at zero overpotential. And what does that mean? So if it's at zero overpotential, we are at the standard potential of an electron transfer process. So for example, our ferrocene 2+ and 3+. The exchange current is how much current is passed through those two interacting with the electrode. For example, iron 2+ being oxidized to iron 3+ at the electrode, and then a different iron 3+ being oxidized to iron 2+ at the electrode. It basically tells you about how fast the electron transfer occurs at the electrode without any applied overpotential. For most systems, this is quite small. You would ideally want this to be very fast, very large number. If this was infinite, then you would have, you would observe Nernst behavior. If it's small, then you would observe non-Nernstian behavior, such as is seen with water oxidation or CO2 reduction, where we can be at potentials much greater than the thermodynamic potential and still see very little current for that reaction. Now, there's a factor in this exponential, which is the charge transfer coefficient, and that relates the reversibility of the reaction. For example, one reactant might be favored, the oxidized form versus the reduced form might be favored, and so those will have an asymmetry. If they're both equal, if there's an equal energetic barrier for both directions, then both of those will be 0.5. So typically they're assumed to be 0.5. Again, we have our typical NF over RT, and then we have this overpotential. So the overpotential is the potential that is applied, and it's the difference between the applied potential and the thermodynamic standard potential. So for example, if the oxidation of water occurs at 1.23 volts versus NHE, if I apply a voltage of 1.53 volts, I've applied 300 millivolts of overpotential. I've applied 1.53, and the standard potential is 1.23. That's 300 millivolts overpotential that I've applied. That's the extra potential I've applied to do the work. And so at high overpotentials, we can rearrange this into the Tafel equation. And we can get several interesting factors from this. One of them being, if we extrapolate this linear region of a plot of the overpotential versus the log of the current, if we extrapolate this to zero overpotential, we can obtain the exchange current. As I mentioned, that can be a very powerful parameter to know. The other really important part is that the slope of this can give us information both about the symmetry of the charge transfer and the number of electrons in the rate determining step, which can be very useful if we're doing mechanistic studies. Now, there are other complications associated with Tafel behavior that can have significant deviations from the form I've shown here. So while I mentioned that the number of electrons in the rate determining step can be estimated, I urge you caution in doing analyses of that type. So, but in any case, a overpotential versus log of current plot of different catalysts can be very informing in terms of inherent catalyst activity and can give you clues as to the electrochemical mechanism. For example, if the rate determining step is 1 electrons or 2 electrons or probably not 3 electrons. It's typically 1 or 2. So I keep bringing up these suggested further readings, but I really encourage you to take a look at Electrochemical Methods by Bard and Folkman. I actually think they have an electronic version available now, but these other papers you should be able to get and take a read if you're interested. With that, I'd like to acknowledge the EC personnel who helped me get this together, my lab group for helping me out, the EU Horizon 2020 who have paid for my fellowship, and you all who have attended. And with that, I'll take any questions.
You were talking about the junction potential. What happens if you have electrolytes with different charges? For example, you also put electrons for electrolytes with 1 plus 1 or minus 1. If you have plus 2 and 1 or something like this, how is it affect?
You mean just for the electrolyte or for the redox species?
No, just for the electrolyte. Well, for the duration of the species.
Okay.
Yeah. I think that you talk about the
yeah. So an audience member asked, how does the charge of an electrolyte affect its migration? Is that correct? Let me see if I can go back in the presentation. So if we take a look at, for example, liquid junction potentials, where there's just a chemical gradient, these are all singly charged ions or cations. Where a change in charge would manifest itself is the difference in the transference number of the, I don't think the people on Zoom can see my screen. I'll share it again. So if we look at these, we can see that these are all singly charged, and the transference number tells us how much current is carried by a certain ion. So if we used a dication and it had the same mobility, it would carry twice the amount of current. But oftentimes, if something's more charged, it has a greater drag in solution because it might hydrogen bond more or have other ions paired with it. Good question. Yeah. Uh-huh. Yes.
So my question is, first of all, the reaction and both cathodes and anodes in the electrochemical, depends on the reaction of the electrons.
Yes.
And then the question is, so when looking at papers that use electrochemistry for separate organic systems, and organic chemicals and biological,
Mm-hmm.
but usually they don't use electrochemistry
Okay, so the question first was, in an example, can the working electrode be used as an anode and a cathode? And the second question was, in some papers, the audience member noticed that authors often describe only using 2 electrode setup. So the answer to the first question is the working electrode can be used both as an anode and or a cathode depending on the potential applied. Now, the nomenclature can be tricky because, for example, in batteries, you always name it based off of how it's discharging. So if I discharge in one direction, the anode is where the oxidation occurs. If I'm charging, now all of a sudden reduction's occurring there because I'm flowing it in the opposite direction, but we still call it the anode. So that's something to think about there, to calibrate yourself on, and you can double think these things and double check what is the spontaneous direction of current flow and what is the precise nomenclature that I'm using. Typically in 3 electrode electrochemistry, when I say anodic, I'm talking about an oxidation. If I say cathodic, I'm talking about a reduction. And the next question was, a lot of authors only use a 2 electrode setup. I think that, well, depending on the precise nature of the reaction that you're studying, it might not matter. So for example, if I'm applying 5 volts and I'm in an acidic solution and my counter electrode is platinum. Well, yes, exactly. It'll be hydrogen evolution at the platinum counter electrode, and whatever other reaction will occur will be at 5 volts versus approximately RHE. Like it might shift around a little bit. That's the disadvantage of a 2 electron cell, is that it will shift around. The exact applied potential at one of the electrodes might move. If you're just doing a bulk synthesis, maybe it doesn't matter because maybe there's not that many other reactants in solution. Another example where we do typically use a 2 electrode setup is in a membrane electrode assembly, where we have the anodic catalyst and the cathodic catalyst in close contact, and we just apply a potential to the overall cell. Now, this is in cases where both electrode catalysts are very well studied and very well understood. So you more or less know what reactions are happening at both of them, and you're trying to minimize the overall cell potential in that case. So when we do ours, we use a commercially available cathodic electrode catalyst, and then we use our synthesized anodic catalyst. Yeah.
But I think when they use the organic synthesis, they apply constant current. So then they don't get out of the voltage, so that's why they reduce everything.
And another audience member brought up a very good point that oftentimes researchers, when they're doing synthesis, will use constant current. Now, constant current has the advantage of you will continuously apply a certain amount of current for a certain amount of time. So if you know you have 10 coulombs of product, you can apply 10 milliamps for however much time, and you know you should have theoretically reduced or oxidized all of your reactant. The problem with that can be that you're not controlling the voltage. So typically in those experiments, they may be faster because your current's the same the whole time, whatever you want, but they will be typically less selective because as you deplete your product, the potential applied at the electrode will continue to increase to meet the demand for the current, and then it'll start to do side reactions. That's also slightly more dangerous. If you accidentally touch 2 electrodes that are applying 1.2 volts, you probably won't even notice it. But if it's trying to achieve 5 amps, you're going to notice it because it's going to apply whatever voltage it needs to get that current. And if that voltage across your body is 40 amps, 50 amps, 100 amps, it'll do it in order to get whatever voltage or whatever current it needs. So that's something to think about too, that constant voltage is typically more selective and a little bit safer.
So it's a kind of specific question. So let's say that you have a Faradaic efficiency that is way over than 100%. And you're rather sure that like you account for all the liquid or gas products. So how do you proceed to understand if maybe your catalyst is like reducing or the process, something like is there a protocol to do? Like,
Yes.
It's complex, I know, but I'm really curious.
Yes, so an audience member asked, let's say your Faradaic efficiency is really low and you're trying to account for all of the products, basically, right?
You're sure that like it's low, but something else is happening, that you are not reducing or oxidizing any products, but something is happening with your catalyst.
Okay, so that's a tricky question, and that's kind of a philosophical question as well. And I would say the most comprehensive approach would be to list out all of the possible electrochemical reactions you think might occur. For example, if I'm doing water oxidation or oxygen evolution, the one I want is to produce O2. Maybe I produce H2O2. Maybe I'm making hydrogen peroxide. Maybe I oxidize some of the metal in the contacts. If I measure 95 plus or minus 5% Faradaic efficiency, I'm going to be super happy, right? But if I'm measuring 20% Faradaic efficiency plus or minus 5, I'm going to be a little upset. And then I'm going to have to ask myself, where's all that extra current going? And so that's when you have to think of all of the possible things that might happen. And so maybe you get a detector or an analytical technique to look for hydrogen peroxide. Or maybe your electrochemical cell is leaking out gas. You know, that's a really tricky problem if you're involved in a gas like hydrogen or oxygen, or if you're doing CO2 reduction, you don't know how much keeping track of all the CO2 you put in, that's going to be hard. But maybe keeping track of your products might be a little bit easier, but maybe you're making carbon monoxide from that process and that's escaping too. So it can be tricky. I would say the best thing to do would be to come up with a list of all possible alternatives and disprove them. Come up with a way to disprove hydrogen peroxide, disprove, let's say, if I use carbon as my electrode, disprove oxidation of carbon, then I have to look for CO2 while I'm doing an oxidation, etc. Does anyone on Zoom have any questions? I suppose no.
Between doing a differential full voltammetry and CV, I mean, if you get the same information as well, which one is
So the audience member asked about differential pulse voltammetry. Let me pull up the slides from last week. So I did not cover differential pulse voltammetry, although it is a technique of mine that I like quite a lot. Let's see. Okay, so if we look at a cyclic voltammogram, we're looking at a linear sweep in one direction and a linear sweep in the other direction. A differential pulse voltammogram you can think about as taking the first derivative of this whole experiment. Now, experimentally, it's a little different than that because you are taking voltage steps and you're looking at the differences in the current. But practically speaking, you're looking at the first derivative. Now, you probably know that the maximum rate of change here is going to be somewhere in the middle of here, right? This is a little bit of a sigmoid. So you're going to be looking at the maximum rate of change here in the differential pulse voltammogram. That's going to be the new peak, right? This is going to come up, it'll peak right here, and then as this decrease, as the cyclic voltammogram continues to evolve, the slope will go back down. Practically what that looks like is instead of having two peaks that are separated, if it's electrochemically reversible, they are on top of each other. Because you're looking at essentially the first derivative of this experiment. The other thing that it will do is it will suppress any effects of double layer charging. Because as we talked about earlier, the double layer charging is basically the same. It's independent of current. It's dependent on scan rate, but it should be linear in the background. Let's see if I can pull one up. If we look at these experiments, the double layer charging isn't changing. So if we do differential pulse voltammetry, then we're able to more, we'll have a greater sensitivity towards our electrolyte at lower concentrations. Also, if there's other peaks that are close together that are not well resolved in the cyclic voltammetry, oftentimes differential pulse voltammetry can be used to separate those two peaks. Because again, you're looking at what would essentially be the first derivative, which would make it more sensitive to changes rather than the absolute current. And there's a number of pulse voltammetric techniques, including square wave voltammetry, that are kind of similar in their approach. Again, trying to develop more sensitivity and delineate electrochemical processes.
So then if this one is more sensitive and more, why do people usually watch it
So the question is, if differential pulse voltammetry is more sensitive, why do people use CDs? I think it's probably for ease of use, because it's easier to understand. I think at least as a first glance, for most experiments, it's typically sufficient. So if proton NMR is good enough, do I need to do G-cosing? It's just a little bit simpler, more common. Maybe you should publish an article arguing that everybody should use differential pulse. I would be happy with that. I like differential pulse voltammetry. Other questions? Well, if you guys have questions in the future, if you want to talk about electrochemistry, this applies to people here and on Zoom. At any point, I'd love to talk about your questions, and we can try to find a solution, come up with a cell design. It's something that I very much enjoy, so feel free to reach out to me, and thanks again, everybody, for coming. Have a nice week.